Last time we have studied characteristic function. Now we shall study equivalence and countable sets. So that is, we shall study equivalence of sets and countability of set. First we shall consider equivalence, and we write it as a definition. Let f from A to B be a 1 and onto function. Then f is called a 1 correspondence. Or 1-to-1 correspondence. And the two sets A and B are said to be equivalent. So this is the definition for equivalent sets. When two sets are A and B are said to be equivalent, if there exists a function from A to B which is 1 and onto. We have defined earlier what is meaning of 1 function and onto function. You refer it. And then such a relation or function exists, then A and B are said to be equivalent. There is 1-to-1 relation and also onto. Means every element is mapped to unique element here. And for every element in B there exists a pre-image. Then A and B are said to be equivalent sets. This relation is A is equivalent to A itself, because we have a function from A to A itself which is 1 and 1. If A is equivalent to B, then B is also equivalent to A. So they are equivalent to each other. And further, if A is equivalent to B and B is equivalent to C, then A is also equivalent to C. So this is the equivalence relation actually between the sets. Now we will consider what is infinite set. We write it also as a definition. So here we have defined equivalent set, and now the definition for infinite set. A set is said to be infinite if for each positive integer m or there is a subset of A containing precisely n elements. So what is the meaning of precisely? Here means exactly. So such type of, this is the definition for infinite set. When we say A is infinite set, if for every positive integer m there is a subset of A containing exactly n elements. We know the set of integers I is infinite. Example, the set I of positive integers. Here the notation used for positive integers is I. 1, 2, 3, etc. is infinite. And we know the set of real numbers is also infinite, the set of all integers is also infinite. So this set satisfies this condition in the definition. So if you consider any positive integer n, say 150, so then, or we may consider bigger number also, 150 I consider, then there exists a subset of I containing 150 elements. It is very obvious because if you consider 1 to 150, then that is the subset of I which contains 150 elements. If we consider n is equal to say 2000, then this set I also contains a subset containing 2000 elements. So the numbers from 1 to 2000 is the set containing 2000 elements. So this meaning is simple of infinite set. And a set which is not infinite is obviously is finite. So if you consider say s is equal to say 1 to 100, then this is finite. It will not satisfy this condition. So the why it is not infinite, because if I consider n is equal to 101, then this set S will not contain a subset containing 101 elements, because it has at most 100 elements. So this is finite. So that is simple meaning of infinite and finite set. Now we define countable sets. So write the definition. We will write the definition of countable sets. So here what we have defined is infinite. Now a set A is said to be countable or the other name is denumerable. If A is equivalent to the set, A is equivalent to the set I of positive integers. So this is the meaning of countable or denumerable set. A is countable if A is equivalent to the set I of positive integers. Now what is equivalent we have defined here. That means the set must be said to be equivalent if there is a function from A to B which is 1, 1 and on 2. Now here A will be countable if there is a function f from I, the set of positive integer to A. So that is, there is a function f, that is f from I to A is 1, 1 and on. Then A is countable, and another is meaning if A is not countable, or if a set is not countable, then it is said to be uncountable. So if a set is not countable, it is said to be uncountable. So thus there are two concepts here, finite and infinite we have seen earlier, which is finite and which is infinite. Now which is countable and which is uncountable, that type of sets. Countable set has a one-to-one relation between positive integers, 1, 1 and on 2 relation between positive integers, then it is countable. And what is uncountable, which is not countable, is uncountable set. Now we will consider example here. The set of now whether the set of positive integers is countable? Yes, because the set of positive integer function will be I to I, and then it is countable. The set of positive integer is countable. Now whether the set of all integers is countable? example is the set of all integers is countable. Here the verb is not are, because it is the set. The set is countable. Which set? The set of all integers is countable. That we shall consider. Now we will have a solution for this. The set of all integers can be written as, so we can list the elements as, can be written as see 0, all integers positive and negative. Here positive integers we have considered, and now we have considered all integers, means -1 plus 1, -2 plus 2, -3 plus 3, and so on. So this is the set of all integers. We have to show this set is equivalent to the set of positive integers. Now we define a function as follows. Fn is equal to n minus 1 divided by 2. N belongs to, or we should consider this as n plus 1. N is odd, 1, 2, 3, 5, and so on. Fn is equal to minus n by 2. N takes value even, 2, 4, 6, etc. So then we may see this f is function, domain will be 1, 2, 3 or 2, 4, 5, means set of all positive integers is the domain of this function f. And this function is obviously 1, 1 and on. Now what will be its images? Then f is a 1, 1 correspondence. F is a 1, 1 correspondence between the set I and all integers and the set of all integers. As we see, for means because, for f of 1, f of 2, f of 3, etc. f4, f5 gives. Now what is f of 1? F of 1, you see, 1 belongs to the first definition. So f of 1 will be 1 plus 1 divided by 2 means 1. So this gives 1. What is f of 2? 2 is in this case even, and therefore minus 2 by 2 is minus 1. And so we have to consider 0 also here, and for that purpose. So the condition should be here n minus 1. So instead of plus, we define first as n minus 1. Now check it. So f of 1 will be 1 minus 1 divided by 2 means 0 by 2, which is 0. And f of 2 is minus 2 by 2 is minus 1. F of 3 from this, 3 minus 1, that is 2 by 2, that is plus 1. F of 4 from this, minus 4 by 2, minus 2. So f of 5 from this, 5 minus 1, 4 by 2, that is 2, and so on. Now thus this function, which is from I to the set, which is function from I to the set of integers, is 1, 1 and on 2, and it gives these images. F of 1 is 0, f of 2 is minus 1, f of 3 is 1, f of 4 is minus 2, f of 5 is 2, and so on. So this gives all the integers. and thus so this set of all integers is equivalent to set of positive integers, and therefore the set of all integers is countable. So thus this shows that the set of all integers is countable, because there is a function, one onto function between positive integers and the set of all integers. Now we shall consider the properties of countable sets. Now you see, if A is a countable set, the meaning is we can count the elements of that set, or we can label the element, first element, second element, third element, etc. And suppose the elements of A may be expressed as, or may be written as A1, first element of A, second element of A, third element of A, and it is not necessary that it is finite, it may be infinite set. So it is infinite set. A is countable, this set is countable because its elements are labeled. Now B, the elements of B we can write B1, B2, B3, etc. So are countable. These are countable. Then what about their union? Then A union B. What will be the union of these two sets, whether it is countable or not? Now obviously we can see that we can write the elements of A union B like this: A1 B1, A2 B2, A3 B3, and so on. So we can count the elements as first, second, third, fourth, and so. Therefore, this is also countable. Is countable. And thus, what we have is countable union of two countable set is also countable. So this is a result. Now there is a general result. Now how many sets union can be considered? So we can consider countable union of countable sets, and then that is also countable. We write it as a theorem. This will be our theorem 1.5. If A1, A2, etc. are countable sets, then union of n takes value 1 to infinity, is also countable. Extension to this result. Consider n number of countable sets, then their union also is countable, or actually countable number. In words, countable union of countable sets is countable. See the words. Countable we have used. And A1, A2, A3, etc. A1, A2, A3, and so on are countable. So these elements are also countable. And what is meaning of union of n takes values from 1 to infinity? That means A1. This means A1 union, A2 union, A3, and so on. This will continue up to infinity, 1 to infinity. So then this is also a union, countable union of countable sets, or countable union. We can count the elements in the union, so therefore it is called countable union. And A1, A2 are also countable sets, and finally this whole becomes countable. So that we have to prove. Now we shall prove the result. We only have to show how to count the elements of this union. The proof of this, let, or we can write the elements of A1 first. A1 as A11, A12, A13 and so on. This is labeling. First set, first element, first set, second element, first set, third element. A2. A2 as A21, A22, A23 and so on. AN as AN1, AN2, AN3 and so on. Therefore, here the meaning is AJK is the kth element of, now which set? Kth element of AJ. See, this is the first element of AM, second element of AM, so it's kth element of AJ. Now we define J plus K. Now we consider the height of J plus K or J plus K is the height. Height of the element AJ. This is the height of AJK element. Now how the height is defined? Just adding the suffix and affix. This is the suffix and this is the affix, upper script and subscript. So this is the height. So therefore, now what is the minimum height? Minimum height of the elements will be this one, 2. And therefore there is only one element of height 2. Therefore A11 is the only element. Only element of height 2. Now, and what about height 3? Now you see A12 and A21 are the elements of height 2. A12 and A21 are the only elements of height 3 and so on. And so on. So if in general, if m is greater than or equal to 2, so what will be the height of the elements of height m? You see 2, there is only one element of height 2, and height is 3, how many elements? 2 elements. So if height is m, then how many elements must be there? M minus 1. So therefore, for m greater than or equal to 2, there are exactly m minus 1 elements of height m. Now we shall count the elements of this A1, A2, AN. And union of all this means the set containing all the elements. Now we count, or we arrange the elements. Arrange or count. the elements in union of an. N takes value 1 to infinity as follows. Now according to their height. Now first element of height 2, A1. Now the element of height 2 is to be considered as A21 first and then A12. Why this we have written like this we will see further. Then height elements of height 3. Now 4 elements of height 4 we will consider A13 first, A22, then A31 and so on. Diagrammatically it can be shown as follows. As below, where the arrows indicate the order in which the elements are counted. So the arrow we will write the elements like this. So first write the elements of A1, A11, A12, A13, A14, etc. Then write below the elements of second set, A21, A22 and so on. Next, third set. Fourth set. And so on. See how the elements are to be counted. First count A1, then go downwards, then count A21, then go diagonally, count the elements of same height, A21, A11, A21, A12, then go to next element by this direction of arrow, A13, then go diagonally downward, A22, then from A22, A31, and next go downwards, then next go diagonally and so on. Count the element, so like this, and from this now you came to understand this. From this you have to go in this direction. Next element will be 1, 5, then 2, 4, then 3, 3, then 4, 2, and then next element, this one, then go down and go like this. So this we have written all the elements of these sets, and all the elements can be counted by this scheme by taking the elements like this according to their height. So this gives the element of height 2, these two are of height 3, these elements of, or the diagonal gives the elements of same height, these are the elements of height 3, these are the elements of height 4, these are the elements of height 5 and so on. So all the elements in the union, whatever the union, infinite union, will be counted by this scheme. So this scheme counts all the elements in union of A. So this scheme counts all the elements in union of an. Here we have written the all elements of union of an, and thus union of an is countable. Thus this set union n takes value 1 to infinity is countable, because actually we have expressed the counting scheme, how the elements are to be counted or labeled, first, second, third, and so on. So we can count the elements in this way, and therefore this set is countable, and this proves the theorem. Now we will consider next result, but that is a corollary. Now what about the set of rational numbers? It is infinite set, and the set of rational number is also countable. We write as a corollary. But before that, you should know what is the notation for set of rational numbers. In usual way, we denote it by q, and how to define it. This number can be defined like this. Number in the form m by n, such that m, n are integers, and condition is n is not equal to 0. The denominator must not be 0. Then all the numbers of this type are said to be rational numbers. Integer 2/3 or -3/7, etc. are all rational numbers. We know it. The rational numbers can be written in quotient form of integers, quotient of two integers. The corollary is the set of all rationals. The set of all rationals is countable. Or rational numbers. The set of all rational numbers is countable. Why it is we have written as a corollary? Because we want to use the above theorem. We shall express the set of rational numbers as a union of countable set. Now we shall prove it. The set of rational numbers can be considered can be taken as, or can be considered as union of en. En takes value 1 to infinity, where en is the set. En is the set of all integers. En is the set. En is the set of rationals, not integers. En is the set of rationals having n as its denominator. N as the denominator, and therefore we can write En as, that is, En is equal to, n is the denominator, so therefore en can be written as 0 by n minus 1 by n, 1 by n, all rationals which have n as the denominator. So all integers with denominator and n we should consider. The numerator will be all integers and denominator is n. So minus 2 by n, 2 by n, and so on. So this is en. Now what will be even then? Even will, now you may observe, even will be 0 by 1, minus 1 by 1, 1 by 1 minus 2 by 1, etc. So integers it will be. E2, 0 by 2, that is 0, minus 1 by 2, 1 by 2, minus 2 by 2, etc. So E3, and thus this gives all the type of quotients, rational numbers having n denominator, and therefore union of en will form the set of rational numbers. Now you see this en is equivalent to which set? This En is equivalent to the set of all integers. And because here the numerators are integers, and therefore the relation can be considered as, so integer 0 is related to 0 by n, integer -1 is related to -1 by n, 1 is related to 1 by n, and so on. So this set is equivalent to the set of integers. Now each En is equivalent to the set of all integers. And we have proved earlier in example, the set of all integers is countable, and therefore is countable. So it is countable. Each En is countable. That the meaning is each En, which is equivalent to set of all integers, and because the set of all integers are countable, therefore each En is countable. And union of En is also countable. Therefore, by theorem above 1.5, so we may consider by theorem 1.5, union of En is countable. And what is union of En? The set of rational numbers. Because we have written the set of rational numbers is considered as union of En, or is expressed as union of En, and thus the set of rational numbers is countable. And this proves the result. The set of rational numbers is countable. This completes the corollary. Now one more result we shall consider is as theorem 1.6. So it is a simple result. An infinite set of a countable set, infinite subset of a countable set is countable. Infinite subset of countable set is countable, that we shall prove. Now let the proof is, let A is equal to say A1, A2, A3 and so on is an infinite set. Is countable. We have to consider countable set first. Is countable. Now let us that means AI is element of A. Any AI is element of A. Let element of B, let B be an infinite subset of A. Let further B be an infinite subset. It is a subset of A. Therefore, every element of B will be an AI. Because B is subset of A means some element from A will be in B. So every element of B. So this will be is an AI. Now here we will consider, now we have to label the elements of B. Every element of B is AI. We label N1 B a number for which N1 is the smallest element of B. Let N1 be a number, or it will be a positive number. be a smallest number. Smallest number, positive number it will be, or positive integer we may say. For which a and 1 belongs to B. And let n2 be the next smallest positive integer for which a and 2 belongs to B. Let n2 be the next. Positive integer such that a and 2 belongs to B, and therefore the elements of B can be written as, therefore B can be expressed as. So therefore we can express B as, write B as, B is equal to first element a and 1, a and 2, and so on, a and 3, etc. And thus the elements of B are counted. So what it says, A is countable, any subset of A is also countable, though it is infinite, B is infinite. And but only how to label the set elements of B, that we have written. So this labels every element of B, and therefore B is countable. So this labels or this counts. This labels or counts every element of B. Therefore, B is countable. And this completes the proof. That means if B is an infinite subset of A countable set, then it is countable. This proves the result. Now, one more result in this section is the set of rationals in the interval 0 to 1 is, all rationals in this interval 0 to 1 is countable. This will be a corollary to this theorem. The set of all rationals in this interval 0 to 1 is countable. Now how will we prove this? So the proof is simple. Now you see, all rationals it should be, so I should correct it. Rationals means rational numbers. The set of all rational numbers in the interval 0 to 1 is countable. Now you see, the set of rational numbers in this interval is the subset of all rational numbers, and all rational numbers we have proved is countable. So therefore it is a subset of countable set, and subset of countable set is countable. So that proves the result. So we know the set of rational numbers is countable. Interval 0 to 1 is the set of rationals in interval 0 to 1 is subset of this countable set. The set of all rationals is all rationals in 0 1 interval is subset of rational numbers, or is an infinite subset of rational numbers. Infinite subset of rational numbers, and therefore it is countable. So therefore, by theorem, last theorem, that is 1.6. By theorem 1.6, it is countable. So this set is countable, and thus this proves the problem. So this is about the countable sets. It is countable. Okay. The remaining part we will continue next lecture. Thank you.